Okay, 1991, question 3. I don't even know if you can find answers to this on the internet. You can if you are, I don't know, you got to be real careful. It's not on the links I'm going to give you. All right, so we have 2ClO2 gas plus 2F2 gas goes to 2ClO2F gas. The following results were obtained when the reaction represented above was studied. At 25 degrees, write the rate law. And so I really like that I can do colors here. Okay, to find the order with respect to chlorine dioxide is you change the chlorine dioxide concentration, but you leave the fluorine alone. And so you can see right here that trials or experiment 2 and 3, this is held constant. This is doubled. I'm hoping that you can see that 0.020 divided by 0.010 is 2. And this one's a little trickier, so you have to get out your calculator, and I always do the later trial divided by the earlier trial. If I do 1.92 times 10 to the second, which is a bigger number than 9.6 times 10 to the negative 3. So remember, I always do the earlier trial divided by the lighter trial. This is approximately 2. So basically, here's what I'm saying. You doubled the concentration of chlorine dioxide. You left the fluorine concentration alone. There's no change. So if the rate changes, it has to be coming from this. And so when this doubled and this didn't change, this doubled. So order means exponent. So the order of the reaction with respect to chlorine dioxide is 1. Now, to find the order with respect to fluorine, you hold the chlorine dioxide constant, which is trial 1 and 2. This is no change. This quadrupled, because 0.40 divided by 0.10 is 4. And then 9.6 times 10 to the negative 3 divided by 2.4 times 10 to the negative 3. Well, this is going to cancel this, and I know that 24 times 4 is 96. So 2.4 times 4 is 9.6. This quadrupled. And so 4 to what power gives you a 4? This is a 1. And so right now, this is what the rate law reaction looks like. It's K, which is the rate law constant, times the concentration of chlorine dioxide to the first power, times the concentration of fluorine to the first power. Cool. Next slide, B, calculate the numerical value for the rate constant. So I like to use trial 2, so let me just do or trial 1, sorry. K is going to be calculated by taking the rate for any trial, I like trial 1, divided by the concentration of chlorine dioxide times the concentration of fluorine. Those are both to the first power. The rate in trial 1 is 2.4 times 10 to the negative 3 molarity per second. And now these guys are downstairs, and so it's 1 over 0.010 molar. And then fluorine is also downstairs, so then this is 1 over 0.1 molar. Just going back a slide to show you where I'm getting that. 2.4 times 10 to the negative 3 is the rate. And by the way, they say initial rate because you know how kinetics works. As this slowly turns over to this, these concentrations go down, and when they're less concentrated, the reaction is slower. So we're always looking for the initial rate of formation. Like they just measured these rates for the first couple seconds, and then it drops off because of the decreasing concentration of this. But you can see that chlorine dioxide is 0.01 and fluorine is 0.1. And so if I go back to this slide, you will see that if you put this in a calculator, you end up with 2.4 is the numerical value. This cancels this, and then this is molarity times second. And so that's K. with units. Fabulous. In experiment 2, what is the initial rate of decrease of fluorine? Now, this problem is very difficult. Kids don't see this. I mean, it's not difficult, but they don't see this. So I want the rate, sorry, that's really bad. And I have to explain why we do this. We use this other formula that you learned in the chapter. Okay, so here, I want the rate. They're asking about the rate of F2. And they're telling you that it's decreasing, which makes perfect sense, because one of the things we've been hammering on in this chapter is that, or in the, I don't know when you're doing this, but usually I assign these problems during the kinetics chapter. So here's our reaction. I'm just copying this down. And so this concentration and this concentration is going to go down as the reaction proceeds, and this concentration is going to go up. And so what happens is, that's why they say decrease. Now, if you go back 2 slides, they gave you the rate of this stuff, and they asked about the rate of this stuff. And remember, the rates are related by the stoichiometry. See the 2 to 1 to 2? So this is disappearing at the same rate that this is appearing, because 2 to 2 is the same thing as 1 to 1. But this is a 1. This is disappearing at half of the rate that this is appearing, because this is a 1, this is a 2. 2 is twice as big as 1, or 1 is half as big as 2. And so remember, the rate, you only need to know the rate of one of the things, and you can use the stoichiometry to get the rate of the other 2. Now, so what happens is, what is the rate of the decrease of F2? Well, the rate is going to be, and I'm going to use trial 1. The rate in trial 1 was 2.4 times 10 to the negative 3 molarity per second. This was the rate of appearance, because remember, the products appear, the reactants disappear, of ClO2. Sorry, I missed this F in here. It's got to be balanced. But they didn't ask about that. They asked the disappearance of this. Well, see that 2 to 1, 2 is twice as big as 1. So the rate of disappearance of this is going to be half of that. And so the answer to the question is, it's going to be 2.4 times 10 to the negative 3 molarity per second, divided by 2, because it has to be half as much. And then, and so you end up with, oops. I'm looking at my answer key. I think I missed something. Hang on. In experiment 2, they want us to use not the rate in experiment 1, but the rate in experiment 2. So that was almost a huge mistake. Sorry. They said to use in experiment 2. So in experiment 2, this was 9.6 times 10 to the negative 3. That's how fast this stuff is appearing. But the question asks, how far is fluorine disappearing? Well, 9.6 divided by 4.2 is 4.8 times 10 to the negative 3 molarity per second is the rate of disappearance. You can say disappearance. Hold on, I got to push pause for a minute. Okay, I'm back. And so 4.8 times 10 to the negative 3 molarity per second is the rate of disappearance. Or you sometimes in the book it'll just say this is negative. The rate of appearance is positive. The rate of disappearance is negative of fluorine. Something like that. Just convey to the graders that you know what you're talking about. You know, there's more than one way to skin a cat. This is my favorite one. Which of the following reaction mechanisms is consistent with the rate law developed in A? Justify your choice. Okay, so here's the first one. Let's look at the first one. Now remember, the rate law comes from the slow step. But if the slow step is not the first step, you have to back sub. So what happens is, if you look here, ClO2F2 is the same thing as ClO2 plus F2. So what I'm going to do is, I am going to rewrite this slow step as, and I'm going to sub in ClO2 plus F2 goes to ClO2F plus F, because if this is the same thing as this in this fast step, in the slow step, because the rate law comes from the stoichiometry of the slow step, but the rate law can only have the reactants in it. So you always have to go back to the beginning. Well, ClO2F2 is equivalent to, think of this as an equal sign, is ClO2 plus F2. So I just sub that in. Well, look at the stoichiometry, 1 to 1. The rate law for this one would be K times ClO2 times F2. And so that one is consistent. Why? 1, 1, 1, 1. So the answer, I think, is this, but let's check this one. This is the slow step right here. If that was true, the rate law would be the concentration of F2 to the first power. But notice there's no ClO2 in there. This reaction mechanism would say that ClO2 does not participate in the rate law. Or in other words, changing the concentration of ClO2 would not change the rate of the reaction. And we can see from the table that that is not true. And so which of the following mechanisms is consistent? Justify your choice. I think justifying your choice is just showing this would be the rate law for reaction mechanism 1. This would be the rate law for reaction mechanism 2. This one is consistent with the data in the table. I would just say something like that. Remember, you're just always trying to convince the graders that you know your chemistry. All right, that's good.